My name is Ben Sykes. I work for Netflix, and I operate the largest real-time cluster that we use in Netflix to make sure that your devices, your TVs, and everything are operating as smoothly as possible. It is one of the biggest clusters that we have, especially for real-time. And some headline numbers, we do on the order of 10 million events per second and a few billion queries per day. It's heavily hit. It makes it difficult to do all kinds of things like upgrades, and I'm going to dig into some of that and how we keep the cluster stable and performant. So this is what we're going to look at today. We're going to build on some core principles. So how do we get to this kind of scale and be able to manage it with a relatively small team? There are only a few people who actually work on the core Druid team. I'm one of their partners. I don't actually contribute directly to their team. I'm more of a user of Druid. So we're going to look at how we use patterns to make it seamless to manage clusters across the board. We're going to look at how we do that management. And this is going to build on some of the ideas that the previous talk talked about. We're going to look at how we leverage centralized logging and metrics, and this is going to be one of your favorite movies here, Inception, where we use Druid to monitor Druid. And then finally, we're going to dig into how we realize we can get the best performance we can and make sure everything's running well with our parallel testing framework. So what does our core architecture pattern look like? All of our clusters look identical at a high level, regardless of their use case and regardless of their scale. They all have the same controller nodes, they all have the same query nodes, they all have the same data nodes. It's just that some of the clusters may have 0 of these things. For example, if we've got a big batch cluster, that will probably have no middle manager nodes because there's no real-time ingestion to be done and very little operating tasks to perform. If we've got a small test cluster, it'll probably have 1 historical, maybe 2, whereas the big production ones will have hundreds. And we can scale individually for the amount of brokers we want to operate and send the queries to different brokers based on their query characteristics. Every single one of these nodes is reporting in the same way. It's doing the same metric logging, the same logging as well. Everything is identical. Okay, but why do we do this, right? Why do we have this pattern? Why do we keep it all consistent? Because we have a lot of clusters. Last I counted, we had 15 distinct Druid clusters. And I mean that as the full collection of all of those nodes, not individual resource groups, as I will refer to them. In total, we use more than 1,800 servers. That's a bit too much to go and patch them individually and keep some kind of mental context about where you got to in an upgrade cycle. And once we can test out and prove out a given config for whatever part of the cluster we're looking at, we can apply that pattern across the fleet, and everyone benefits from it. I mean, that's a little hand-wavy, of course, right? Things have to be tuned depending on the use case. So how do we do this? Right. As the folks earlier were saying, we use immutable infrastructure. So we don't go and log into the machines and upgrade and patch them and edit configs. Strangely, perhaps, we use a single image for every role in the entire cluster. So that's the same underlying image for a router node and the same underlying image for a middle manager node. Like, they're doing very different jobs. Why is it the same image? But we'll come on to that later. If something's misbehaving for whatever reason, we will trash it and replace it. We're not going to log in and debug. Well, we will debug. We're not going to log in and try and repair that node. We will choose to terminate it and replace it rather than fix it. If something's underperforming, we will scale up. We'll add more nodes. And we'll let Druid do its magic behind the scenes and integrate that node into the cluster without us having to do anything. All of this is largely built on this pattern model. So every single one of these resource groups so like your historicals and your middle managers, is all determined based on the naming convention. And then to seamlessly integrate and roll all this out, we lean on heavy automation. So again, as the folks earlier were saying, we use blue-green deployment, so we'll create an entirely new cluster, get it all ready to go, and then trash the old one as we switch over the queries. So I'm going to acknowledge a few things here. A lot of how we get to this is coming from a very privileged position of being in a large company and having years of people building the tools that we're going to build on top of. Things do exist in open source. I'm not going to name any here today, but you can find your own, I'm sure. So immutable infrastructure, as a quick recap, what does that mean? So in a traditional server farm, you might log in and do updates. You connect, you would edit, you would update, you would restart. You can do rolling restarts in this way. And you may even script this if you want. So you've got a new version. I don't think the colors come out quite so obviously in this chart as I was hoping, but you can see that the third node in the resource group there is running a different color. So the new version maybe. This leaves you in an inconsistent state. You've got some nodes in your resource group that are on a new version running a different config, and some that are running the previous config. So it's hard to reason about what's going on. In an immutable pattern, you would duplicate the entire cluster with the new version and then tear down the old one once you'd switched everything over. So we create a new image, we then deploy that, and then terminate the old ones. Again, this is, at scale, this can be a privileged thing because it's not cheap to run an entire duplicate cluster. So as I said earlier, we run a single image for any role. And I put an asterisk on this because today we do this with AMIs. So we're deploying onto EC2. We create an AMI. As part of our management, it's easier for us to reason about and see in our UI, which I will demonstrate later, that everything is running on the same version. We know that it's a clean slate. If we were doing this with containers, my opinion might change whether this is the right approach, because containers can layer in those additional config changes, and you could make a smaller image that's more appropriate to that individual role. But for now, we make the image is appropriate for any role in our cluster. So it keeps it simple. We build it once. We don't have to build many images, and we deploy it many, many times. So not only can this single image be used in every resource group within a cluster, it can be used in any resource group across any cluster. It's got all of the configs it needs. It's got all of the code it needs to run anything we want. So as I said, we use this resource group naming convention, which I'll also show you later. You don't have to imagine it, to work out what node I am, therefore what role I need to do, and what config I need to apply. And then under scaled, add more nodes. Let Druid handle the registration of that node. It will come up. It will tell whichever appropriate controller it needs, the overlord or the coordinator, and say, I'm here, give me work to do. And that is dead solid. It just works. It's great. And that's all down to Druid. It's not any of our infrastructure that does that. So you should be able to do this with whatever setup you have as well. So what does that look like? What does add to scale up look like? Here's an example. So say I was looking at our Druid cluster, and I see our int ops middle manager node here that's doing too much work. It's full. It's lots of full. Its backlog is building up. I come to this very specifically named resource group that is cluster name, job role, tier. I can come along and say, resize this. I want to add another node. So I say, go ahead, add one more node, and that is that. It will provision that same image on a new instance. Because of its naming convention, it loads its configuration, bootstraps itself, registers with the overlord, and becomes available. So we can do this because all of these images are the same. We could do it even if we were using container images, but the idea here is that it's trivial to add a new node and scale up as appropriate. And you can do this on individual resource clusters within your individual Druid cluster. So we come back to Druid now, and it's already registered. We've got 2 int-ops, and it's already full, working on the backlog of tasks it had to work on. So we also have the opposite problem here, right? So if, as I said earlier, something's misbehaving, we can come in and we can terminate. And then our resource monitor, our health monitors that run within the framework will realize that that node is gone, and it wants maybe 80 nodes in the historical tier, but it's only got 79. So it'll go mint a new one, do the deployment for us without having to manually scale up. And again, that will register with the overlord appropriately, and all of the self-balancing of data segments will take place behind the scenes. Nothing we had to do for that other than the monitoring and replacing part. So to do this, we automate everything when it comes to replacing entire server groups. So replace entire clusters. This is not supposed to be an eye test. This is just a background to show roughly how complicated it is to deploy a Druid cluster. So when it's time to redeploy, whether we've made a config change or Druid version change, we trigger this pipeline here. This allows us to select the Druid version we want from a specific branch or specific build, so we can try out the current configs with a new Druid version. Or we could have patched something potentially and want to try that out. We can also select the config branch and the config version. So this allows us to commit our configs and try them out before they're merged into the main branch, and allows us to copy or slice and dice kind of thing with different Druid versions, different configs. This is a building block for how we can be flexible with the cluster configurations. So this whole pipeline from nothing to a whole new Druid cluster operating and queryable takes a variable amount of time, depending on what it's doing. In the normal case with historicals and middle managers, it's somewhere in the region of an hour. It can take longer if there's a lot of historical data to load. In the best case, with no middle managers to stop and wait for, and a smaller data set, it could be the order of minutes, maybe 10, 15 minutes. So as we go through this pipeline, we first bake that new image, which has got specifically the Druid version and the configs we want to try out. We then go deploy the historical nodes, create all of the storage devices, attach them all appropriately. We then deploy the coordinator to get those all registered. We ripple through here. There's a few manual gates that we can skip or not, depending on whether we want to wait for all the historical to backfill or not. And we get to a critical point here where we have to shut down the Kafka indexes. So we haven't yet found a clean way, and a clean and safe way, to be able to do a blue-green deployment without pausing ingestion momentarily. The way we get around that is, again, a very privileged way of getting around it. We run an entirely duplicate cluster, but it's a bit smaller in a separate region, which we use for disaster recovery as well as deployments. And when we're doing this deployment in this region, we'll actually switch the queries entirely to the other region, so this one can take a little bit of downtime without interrupting the live feed of real-time data. So we do that pause, and then we have to wait critically for all of those middle managers or the indexing tasks to complete. If we don't wait for them to complete, what happens is the new overlord and the new middle managers will pick them up and start running them on the new cluster as well, and then they get terminated eventually, and we end up actually losing data fairly consistently if we do that. So that is a gotcha that you need to watch out for if you're going to try and do any of this blue-green deployment. Once that's done, we can then enable all of these nodes, which is effectively putting them into DNS appropriately. And then eventually, we can restart those Kafka indexes and terminate the old cluster. So there are some manual points in between this where we can pause if we like to do experimentation, which I will dig on in a moment. But the key point here is that to be able to do this automation, you need to have a solid foundation of good architecture patterns that are similar across all of your clusters. Otherwise, you'll end up replicating this pipeline for every cluster you work on. It needs to be reproducible. It needs to be dead solid. Fail if it's going to fail. That's fine. You can undo and clean up. But continuing in a failing state is the worst thing for this kind of deployment. So another core principle we have here is our centralized logging and metrics. So every single one of our Druid clusters, regardless of their task, all log to a central point, and they all emit a metrics to a central point. So these are the metrics of how Druid is performing. We choose to use Druid for our in-field monitoring because it's great at doing metrics. So why wouldn't we use Druid to monitor Druid? Because it's still just metrics. So we emit these metrics over Kafka, ingest them in the same way we do with any other real-time ingestion into another Druid cluster. And then we have alerting and monitoring and everything built on top of that set of metrics as well. And then you might ask, what happens if that cluster breaks? Well, we have another one that monitors that one too. It doesn't go on indefinitely. We stop at 2. But we genuinely do have a very small cluster that's sole job is to monitor the monitoring cluster. And we have alerts on that. Who monitors that? Well, our alerting system monitors that. And if it fails to report any metrics, we also get an alert. So yes, this is our inception joke here. And having Druid ops metrics in Druid is the way to go. I think the very small one is actually very small. It might be single instances for everything. Okay, so how do we know if a config change is effective? This is building on the top of all of that background, right? So given that we have the ability to apply any Druid version with any config change, we can deploy in parallel duplicate clusters. Only one of them will be serving queries to the actual users at any point. And that we have our metrics aggregated into a single point where we can query and compare. How do we get on to validate that a config change is effective? So we could do before and after. We could take a measurement of how the cluster was performing, whether that's query performance, resource usage, or anything else you might want to look at there. And record how that went, and then try and replicate that again after we've deployed it with the new cluster, which is fine for big wins. If you're looking at a 50% reduction in query latency, for example, you're going to notice that. That's fine. But if you're looking at micro wins, can we run a few less indexes for this particular ingestion path? Or can we put more indexes onto a given middle manager, for example? Squeeze more resource utilization out of those nodes. That's more difficult to do in a before and after comparison. It's more difficult to do squeeze testing, where you're trying to take as much data as possible and shove it through as little as possible and see where they break. It's hard to do load testing, where you're putting way more stuff in the same amount and seeing how big your cluster can handle before it falls over. So the best way, in our opinion, is to use an apples-to-apples comparison. This is exactly the same way we do our updates in the field for real production applications. We will deploy a new version, a small amount of users to that new version, a similar amount to the current version. We'll record all the metrics into our main Druid cluster, and then run an A/B test effectively, and comparing these and do an analysis and say, this one is different from this one in these ways. So why don't we do that with our Druid configuration as well? So we built tools that we can do record and replay for primarily the before and after case. They didn't work out particularly well. We still run some of this on a cadence against some test clusters to make sure that we're not having big regressions. So we'll hammer our test cluster with prescribed queries daily at different points throughout the day. a lower ingestion rate overnight and a higher ingestion rate during the day when people are watching things, and make sure that the performance generally is okay. We've segregated these queries into very distinct groups. So there are some that are dead easy and will hit cache. There are some that will skip cache and always go to the middle managers. There are some that will do a hard query across the full time range or do a massive group by. And we can see how these are performing as they're going through this. We actually run a pipeline to do this. But we recorded a set of queries and we were playing them consistently against different clusters. We also built a tool that allows us to mirror and measure. So by this, what I mean is we've duplicated our new cluster, the new one's up and running, but it's not receiving any queries, right? Because we've sent the queries to the old one still. So how can we give it the same load and then do a direct comparison for how these nodes are working against the old nodes? So we have this mirror. Now this is used to copy those queries effectively in real time, send them to both clusters. The users only get the answer to one of them from the existing production cluster, but we're loading the new cluster in exactly the same way. It's got the same queries at the same time of day with whatever different config change it has or whatever different Druid version it has. But we have now an apples to apples comparison where we can say this one is objectively better or worse than the other one. And therefore, if we made only a single config change, it's probably attributable to that change. And we often run this mirror as a basic smoke test. So whenever we start up and do a blue-green deployment on a new cluster, we'll run this query mirror for a few minutes just to make sure that things are actually performing at all, not only performing well. So what does this look like? Hopefully you could have imagined this from my very detailed description, but here's a pictorial for you. So user queries will hit that existing cluster, the bluish purple of the blue-green. That's emitting its logs into the centralized log store. It's also reporting its cluster metrics into the Druid monitoring cluster there. The query mirror then tails those logs from the centralized log store. And we do this at the moment this way to avoid the old cluster having to know anything about the new cluster or any other testing-only infrastructure. It's logging those logs anyway, so we may as well piggyback on them if we can. We'll then extract the query from those logs and replay it against the new cluster. And there's some nuance to that, which I'll go into in a moment. And then that new cluster also reports its metrics to the same Druid cluster, and then we run some statistical analysis against that to say whether the metrics coming out of the new cluster are better or worse or identical to the old cluster. For some of the bigger wins, as I said earlier, you could eyeball it and say that, oh yes, this is obviously better. We're getting queries responding way faster or fewer errors or something like that. But when you're talking about nuanced things, you really need to run some stats against it to prove that. So we built on top of our cluster architecture patterns and our automated deployments to be able to have similar clusters. We're using our centralized log and our centralized metrics. And then with some relatively simple tools, I mean, these are single instance images that run a Node.js task that do the log tailing and replaying. We're able to then do this parallel testing and build on top of our existing stats models that we use for real productionized application updates to prove that a configuration is better than the other one. And we run this every time we update the Druid version as well. So when we upgrade to 31, hopefully in the near future, we should be able to prove that it is faster and more efficient than the current 29 that we operate. So we're able to do this query performance, query response performance. So that's looking at latency or overall throughput. And resource utilization, are we managing to get more queries through the same number of nodes? Can we use fewer nodes? Are we able to ingest faster? that kind of thing. So I mentioned briefly about squeeze testing earlier as well. So that's trying to use a smaller cluster for the same amount of data, or get it down to a point where you've squoze it so much that it doesn't work anymore. And that's your absolute maximum throughput for that one particular type of task. And we can do this by just scaling down the individual resource groups or by deploying a deliberately smaller cluster. So load testing is about throwing more queries or more data at something. So we do this in a couple of ways. One way, which is the most simple for us, is to run the query mirror multiple times. So just doing a plain mirror, you'll get exactly 1x copy of the live queries that are going into the production cluster. But if you run 2 or 3 or 4, then you're going to get 4x. It's not perfect, of course, because those repeated queries are more likely to hit cache. So we can do things where we can stagger them if we want, or we can modify the query in some way to introduce possibly a different dimension value, or change the time window that's going through there. This is all configurable to allow us to abuse the new system however we want. So this is what we use to try and right-size our resource groups. So do we need 80 historicals? Can we get away with 60 and still achieve the query performance we care for? And we also use this for going through loops and trying to find the optimal configurations for things. This could be down to individual peon configurations. So when you're submitting your indexing tasks, how much memory do you need to give to each peon before it's going to break? How many CPUs should you be giving that? Do you need to allow it to use the entire machine? There's all kinds of small things that you can tweak in there that have quite a big implication. We had one, my introduction said that I like to break things, and I do. We had one interesting outage where we managed to get an increase in indexing rate because of a surge of logs came that managed to take out a bunch of queries. It's like we didn't think this was possible, but it meant that indexing was taking so much resource on these indexing tasks that we could no longer do queries anymore, even for unrelated data sources, because the CPU is being consumed, and we hadn't constrained it to say that this indexing task is only allowed to use like 4 or 5 CPUs or something. So these heavy workload indexing tasks were using a lot more of the machine, and then the queries were failing on unrelated data sources because they had no resource remaining. So this was one way we helped prove that that fixed it. So some gotchas. Tailing logs through an aggregator does add some latency. And we see that the way our log aggregator works is we'll get them delivered in a batch. So if you effectively do a tail over the network, you'll get delivered tens of logs at a time, as a quick burst, and then nothing for 30 seconds, and another batch comes in, which is not how real queries arrive into your Druid cluster when they're issued by regular users or even automated tasks. So how do we fix that? We fix that by deliberately adding some latency to this. So we will stagger the queries and reissue them maybe 1 minute later, maybe 5 minutes later. We can control this as we need to, but then we'll replay them at the same speed. So we keep a buffer of the queries in this query mirror and replay them at the same rate, but not necessarily at the same time. This makes the analysis a little bit more complicated. We have to time shift one of them, but not the other, but it is predictable and we can do it consistently. Some other interesting things. So a Druid SQL query actually gets logged twice. You get the original SQL query, which we can replay, and we get the native query that was derived from that SQL query. So we have to throw that away. Luckily, we can detect this fairly easily because it's logged with a SQL query ID for the native one, and we can see that then therefore came from a SQL query, and we can throw it out. Another very interesting thing here is that logs are emitted at the end of the query. So if they take 1 millisecond to run, probably unlikely, we're going to get that log very quickly. If they take a minute to run, then we're going to be already a minute late before we even try and replay it or buffer it. So that for longer duration queries or for clusters that support longer duration queries, we have to have more of a buffer and more of a delay in order to do the direct comparison. Failed queries are also logged twice. You'll get the query with an error or the success false, and then you'll also get a query with an exception in it. And again, this is relatively easy to catch. If it's got an exception present, we throw it out because we've already worked on it with the success false. Now, this led to another gotcha that was interesting to debug and fix. We were seeing what we thought should have been a more performant cluster actually degraded compared to the less performant cluster because there are a lot of failed queries going to the primary cluster. The new replacement high-performance cluster was succeeding in all of these queries, but because they were succeeding, they weren't being retried by the client, and they weren't being timed out or errored out on the other nodes that could process it, but the others had already failed. So the new cluster ended up doing significantly more work because it was doing the original query and the retry and was working for longer than the timeout, or longer than the previous one had timed out in before. So it was just doing a lot more work, and it wasn't failing though, which was the good thing, right? So it was doing a lot more work and not failing, but we realized that this was a problem in our mirror. So if we get a query that was hard and failed on the source cluster, we have to deliberately set a timeout on that when we replay it to the target cluster so that it's not doing deliberately more work, because it can, than the source cluster was. Otherwise, we don't have a direct comparison anymore. And again, to realize it is expensive and time consuming to run a second cluster. If you want to run this for a day or a week, then that's a double cost for a day or a week. So we don't run long duration tests like this very often, at least not at full scale. So that's something we need to work on, because this is a really nice tool that we'd like to run frequently whenever we're anticipating making any change, but it is a bit too expensive to do that. So what are we looking at next? We're looking at a way that we can try and isolate tests to an individual node or just a few instances. It's like, can we take, if we're targeting just tuning a historical node, for example, or the configuration on a historical node, can we take one historical node in the new cluster and have no other cluster around it at all? Load it with exactly the same segments that came from the main primary cluster, and then target that with exactly the same queries and do it at a micro level. We don't know yet. We haven't tried this. But it's an idea that we're thinking of. And if it works, it will be very powerful for doing very targeted configuration changes or very targeted version changes. I see a hand.
It sounds like another gotcha is you can't make changes to the data compaction or anything like that, since it's a read replica of the original cluster, right? So you can only change test configurations, but not data changes.
That's true. So the question was, we can't really make changes to the compaction or the data configuration because the second cluster is effectively a read replica of the primary one, which is true. Yeah, whenever you change a compaction config, it's going to overwrite those segments. And we do maintain the same metadata store between both of these in most cases. We can stand up an entirely new cluster with a new separate metadata store, but we don't do that most of the time because it's extra work, and playing with Zookeeper is horrible, so we don't do that. So yeah, we haven't actually proven that out yet, but in our disaster recovery side, we often experiment with the dark cluster that's in the other region, and we'll try out different configs there at a cluster level. And then we do a region-to-region comparison. And our query mirror is able to mirror across regions as well. So we don't necessarily need to do a blue-green in the same region. We can do different regions. It's not ideal because there's certain noisy neighbor things that go on as well with that. I mean, we're not supposed to have noisy neighbor problems in AWS, but there's something that goes on where the cluster in the bigger region doesn't perform quite as well as the cluster in the quieter region for some reason. But yeah, that's a very good point. So the other thing we'd like to do is lose the latency and the batching that we have to get from this centralized log aggregation and go to some kind of direct query feed. So we like to store all of the queries that we receive anyway in longer term storage so we can run analytics on the queries themselves and understand how users are using our clusters. Like, can we throw those queries directly onto some Kafka topic or something and then be able to replay those directly rather than having to go through the log store and get the latency and the batching and all of the duplicates that we don't really care for. So we also haven't tried that yet because that would kind of break our idea of not having the old cluster know anything about other clusters to a point. We don't want to deliberately inject test-only code to a production system. I guess there are probably some benefits to that too. So these are the things we're going to experiment on next when we get a few minutes to try them out. If you've got any more ideas of ways that we can improve this, please shout them out.